In this video, we're going to work our first example with conducting a static analysis, and we're going to use a scenario that we saw a little bit earlier. Here we have two kids sitting on a seesaw, and assume at this point that they are not moving, they are not rotating, but they're perfectly balanced in a static condition. And so we begin our process by drawing a free body diagram, and here I have a rigid bar that represents the actual bar that the two kids are sitting on. And the next step is what I need to do is to draw my coordinate system. And because the bar is perfectly horizontal, I can use my regular XY coordinate system where any vector pointing to the right horizontally is a positive value, any vector pointing upward vertically is a positive value, and rotations counterclockwise are indicated as positive, and implicitly the directions that are opposite to these will be indicated as negative. So I have my rigid bar. Now typically we do not draw the external contact. The central pillar that the bar is connected to is considered an external contact, but I like to draw a shadow or silhouette, very light image of a fulcrum, just so I have perspective as to where that external contact is. So I begin by putting into the free body diagram my forces, and so I'm going to start on the left hand side, and here I have the one child here, and the force acting on the bar from the child is gravity, and so I'm just going to label this as force with a subscript number 1 for convenience purposes. Now I'm going to move over to the far right hand side, and I see the other obvious external force, which is the child on the right, and I'm going to label that force F2. Now because the bar does not move in a linear manner, it is constrained by the fulcrum. We know that for the bar not to collapse, that fulcrum must be applying a force to keep the bar from collapsing. Therefore the force must be pointing upward. But I truly don't know if that external contact, which I'm going to call a reaction force, is positive. So it might make intuitive sense, but I truly don't know until I conduct the analysis. So I'm just going to make a guess that it's pointing in the positive direction. One important element that we need to follow through here with systems that have a fulcrum, and with a fulcrum, the fulcrum will allow rotation, so this is a pivot type of joint, is that forces will induce a rotational effect, and mathematically that's called a moment of force. And so I'm going to label the moment of force for each individual force with a subscript. So this is the moment of force generated using the subscript label F1. So F1, it's a linear force that will induce a rotation. That's what the moment of force is. And that's going to be a function of the magnitude and direction of the actual force applied, and that's the weight of the child on the left hand side, times the distance of that force application to the point of rotation, and that line that measures the distance is a perpendicular line at a right angle. Now in this scenario, the force, which is perfectly vertical, and the bar, which is perfectly horizontal, naturally makes a right angle, so the distance just happens to be the length along the segment from the applied force to the point of rotation. Now let's talk a little bit about the reaction force. So the reaction force does in fact have its own moment of force. So recall that every force, provided that the system has a point of rotation, will generate a moment of force due to this equation. So the reaction force does generate a moment of force, and that magnitude is 0 Newton meters. And it's important to note that the value of 0 Newton meters does not mean that there's no force. There is clearly a reaction force. It's just that the moment arm is 0, and if we enter a 0 for either one of these two factors here, then the product on the left hand side will be 0. So this gives us a general rule when it comes to rotating systems. If the vector, in this case this vector represents a force, is sitting on a line of action, now I didn't draw it here, but there's an imaginary infinite line of action that this vector and all vectors will sit on. If that line of action cuts right through the point of rotation, there is no physical separation, there is no perpendicular distance. That distance is 0. Therefore the torque or the moment of force, and I'm using those terms interchangeably, will be 0. So F2 will also generate a moment of force. According to this equation, I just ran out of room on the slide to write out this equation, but we would have a moment of force likewise for F2, but we would just write this out and substitute the number 1 in each instance for the number 2. So now that we have our free body diagram set up and labeled, we're now ready to move forward with our equations of equilibrium. And we start with the special case of Newton's second law, that the sum of the forces will equal to 0 because acceleration is 0. And we always start with our x forces. So we begin by writing out the equation for Newton's second law, in that the sum of the forces acting in the x direction will equal 0. And because in our scenario we obviously see no horizontal forces, the only forces acting on this system are perfectly vertical, then we would just leave it as such. There's nothing to fill in on the left hand side, and we would just conclude, according to our diagram, that there are no applied horizontal forces. That means we're ready to move on to our next equation, which is the same equation of Newton's, a special case of Newton's second law, but we just substitute the y direction for the x. Now we go back to our free body diagram. We start on the left hand side and we start to work our way from left to right, and we look for all the forces that are directed in a vertical manner. And the first force I encounter here is F1. And when I move from left to right, I see another vertical force called F reaction, because we labeled it in our free body diagram. And we keep moving and we have F2. So now I'm ready to rewrite this equation specific to my free body diagram, and we always move the 0 to the left hand side. So we start with a 0. We know that the value will be 0 when we add up all the forces, and that's going to be equal to negative F1, because F1 is directed in the negative direction, and we know it's negative because we go back to the rule we stated at the very beginning, that our coordinate system will dictate the directions. So I have a negative F1, I move towards the right, I encounter another vertical force, which is F reaction. Remember, this was a guess. It seems intuitive, but we just guessed positive, and we put plus F reaction, and because this is a summation, we add the next vertical force, and it's an F2. So I put this in parentheses, negative F2, just to indicate that the summation means that we're adding up, so we're adding negative values. So we see two negative values, which we can, if we were provided with numerical values for the weight of the two kids, we could calculate F1 and F2, but F reaction is the unknown force. So we transpose F1 and F2 to the other side, we rewrite our equation, and what we see here is that F reaction, the magnitude of this force, is going to be equal to the value, the magnitude of F1 and F2. You don't have to indicate negative here. They're obviously going in the negative direction, but we had factored that into the first statement, and the mathematics will just deal with the negatives and the positives, and we just carry forward because when we transpose F1 and F2 to the other side, the negatives become positive. So when we end up with a positive value for an unknown force, that means our initial guess on the direction was correct. If I had guessed a reaction force going in the opposite direction, I would have ended up with a negative value, and if we end up with a negative value for our unknown force, it means our initial guess was incorrect, and we need just simply to reverse the direction, and we use that as a check with respect to our original guess. The last step here is to apply our equation of equilibrium for the moments of force, and we do this because we have a rotating system. There's a fulcrum, and those will be equal to 0. So now we find all of our forces that have non-zero moment arms, and we have the moment of force due to F1, and I had written that out here, and we're going to add that. The reason we add it is because we have the summation symbol to the moment of force generated by F2. Notice I didn't put in the moment of force generated by F reaction. I could have written that in as well, but we already established that that value is going to be 0. Not F reaction, but the moment of force due to the reaction force. So I'm not going to put in at this point the negative or positive values, but I'm just going to substitute the right hand side for the moment equations. So the moment due to F1 is the magnitude of F1 times its moment arm, and that quantity, once we find out this product, we're going to add that to the product of F2 times its moment arm. So obviously we see two negative forces, and we have a perpendicular distance that's going in the positive direction, and we have a perpendicular force going into the negative direction from the fulcrum. I didn't factor that in yet here, but when we start working numerical examples, we will account for those negative directions. But at this point, it's important to note on the moment equation that each of the moments will expand into a force times a perpendicular distance. So this ends this video on our first example of setting up the equations of equilibrium.